Right, so I'll be talking about limitations of database price discrimination. And so I'm from UCSD Economics and with my colleague Denis, and also from UCSD. And also this author was a student at UCSD a year ago and just graduated in 2023. And so there's three of us. Okay, so right, so something about this paper, I would say, like, I thought this this is a great conference where you kind of have all kind of people that speak English in different jargons that probably means the same thing. That is something I realized that, but then and so you might see some of the I mentioned some of the jargon later today, because we had some struggle with trying to find the right terminologies because it does cause a lot of confusion, and we're gonna talk about it later. I will start with classic monopoly pricing. As the title is a database price discrimination. So we'll just begin with the classic pricing theory. I mean, this is probably something that you would take from like the first year IO theory of IO, your graduate sequence, or maybe even in your undergrad classes of pricing. So the setup is very simple. Just a buyer was unit demand, and then was a privately known valuation, and then a covariate X. And so the seller does not know the valuation, but the seller does observe the joint distribution of F and F by X. And so, I mean, it depends on the setting, the seller might not be able to price discriminate. If he or she can price discriminate, and then we just condition on the X, right? So, the situation, you might not be able to price discriminate, or like where sometimes X might be corresponding to some protected characteristic, and there's some constraint that does not allow that. Okay, so, obviously, if you cannot really condition on X, and then it's the optimal thing to do is just to charge a uniform optimal pricing. You take the price times the willingness to pay, right? The percent of people that is willing to pay above the price fee, and then you try to maximize that, and then that gives you the optimal pricing. Okay, and so when price discrimination, which I call a 3D because it's a third degree price discrimination, and if the seller does observe the X, and so that whole strategy is essentially just you condition on X and you charge the optimal uniform pricing. So in the classic setup, like the result says that the 3PD is at least as good as uniform pricing. And you can see why, because the 3PD is essentially an unconstrained problem that you're charging different price depending on the X, but uniform pricing is you charge the same price for all different X. Okay. So that's what the classic theory says. And so I am actually a statistical learning person. So I'm interested in taking stuff to the database, for example, it's Haitian, and so I've been looking at the database monopoly pricing and asking the question, what if the seller does not observe the joint distribution of Y and X, but does have some ID sample that join from this distribution? And so we'll be considering a setup where X is continuous, meaning the fact that if your X is discrete, then the problem is kind of simple. Let's suppose you just have a few discrete, values for X, is a few discrete values. Essentially, what you do is just you condition on that discrete value, and then you do it in pricing. So the sort of theoretical analysis will be rather straightforward. So the difficult part is when you assume the covariate X is continuous. And so one of the other reasons is mathematical challenging and more interesting, I guess that's one of the reasons. But another reason is there is some kind of a motivation for why you're wanting to assume X is continuous, because in practice, people often, like firms often use like one-dimensional continuous form, okay, of characteristic, zip codes, and other information. So the research question we're trying to ask is that, is it too obvious that the seller should engage in third-degree price discrimination if the seller set a price based on the data, on the sample? So the IEs. All right, so I'm just gonna give you an overview. So what we're doing is like, if you guys have attended yesterday's plenary talk, the second plenary talk by Belton, that he talks about the generalization error. So what we're really doing here in this paper is essentially we're looking at the generalization errors of revenue. I'll detail more later on, but that's just, from a learning perspective, that's where we're essentially trying to learn the optimal price function. Okay, but I think if you're on a different community, like say if you're in CS, you might be calling different names like regret, I guess. So that's what we're doing. But what we're showing is that, the later I'm going to propose a very simple 3PD strategy. That it's a 3PD empirical revenue maximization. This is called ERM. This is not the empirical risk minimization. This is the empirical revenue maximization. And by the way, I'm not doing a literature review in today's talk because the time is limited, but if you're interested in what's going on in this literature, we have about 2 pages of description of literature papers. Talk about the paper in CS and talk about the paper in Econ. Pretty much just talk. I think most of the paper on empirical revenue maximization are on CS. Okay, so basically we're going to show that, and it turned out this very simple logarithms has some optimal property, and this optimal is in terms of rate of convergence in revenue to be generated by the true distribution speed to the outcome. Okay, and then we're gonna. So in order to show the optimal, what we do is that we derive a lower bound for the revenue, and what I call it revenue deficiency, it's more like a sort of revenue regret, or what we can call it generalization errors in any database price strategy uniformly over a pretty large class of distributions. So this is a kind of like in statistics we call it max lower bound, but I think in economic theory that people will not like. But that's one thing. So basically it's like one of the exercises you show a min-max lower bound, which sometimes people call information theoretic limitation, and you show there's some kind of strategy that achieves the lower bound. Where you got a lower bound and matching upper bound. So you claim the strategy is optimal. It's that kind of exercise, pretty much. So sort of the important message here, the important economic message here is that absent uncertainty regarding probability loss, 3PD is at least as good as uniform pricing in the classic setup. But in here, the comparison is not very clear. There's not going to be a clear winner. So that's kind of the takeaway message. Right? So I'm just going to give you a classic setup where I'm going to denote. So we're going to assume y and x are supported on this 0-1 interval. And I guess that this is what you do, huh? Well, that's just funny, like this is just really slow. Okay, so we're gonna have this holographic via the setup pricing function. Essentially what this means is that the setup price is gonna be able to depend on the covariate. So this is like set of all possible 3PD strategies. And if we're talking about the uniform pricing strategy, set of uniform pricing strategy, obviously they can charge the same price for all x, and so basically the P is a the classical, more on the classic setup, then here's a definition of revenue at a given point x. It's just willingness to pay times p. And then you get the expected revenue because you're looking at people with different x, so basically you integrate over f of x, this is the density function of the covariate, and it's continuous as I was saying. And uniform pricing is much simpler because you charge the same price for all different values of x, and here we go, it's just a p times the filters, okay, at the price speed. And then, so here's the, oops. How do I do the?
Control L.
I'll turn back. All right, so what is this? Okay, so this is our definition for the true distribution optimal pricing scheme. This is basically the one that did maximize the and integrated or expected revenue with the values that expected revenue. And this is just the PU star is the true distribution optimal uniform pricing that optimize this revenue. Okay, so it's kind of clear like that why the third degree price discrimination is always no worse than minimum pricing if you know the truth. Okay, so here's basically some notations that they're gonna sort of use later on. So when I talk about the third degree price discrimination based on data, I'm basically talking about strategy that we're gonna construct from the sample of yi, valuation data, and xi, which is covariate, and drawing from this distribution, which is unknown to the seller. And then we're talking about uniform pricing strategy, basically just utilizing the valuation data. Okay. And so because you can condition on X naught in the database, for example, base 3PD, so essentially you can sort of say, if this is your database 3PD, and then basically you're looking at when it's validated at a whole year value of X naught, and here's this. And for uniform pricing, you can obviously also think about what is the price at X naught. Obviously, for all X, it's a uniform price will be the same. Okay, so again, so we're gonna do this, like I have this notation, we have the set of all database 3PD and use check. You check the set of all database uniform pricing function. Right, so this is the simple algorithm that's telling you guys. So if you're thinking about setting a price based on ID data, so what we do is that we're just gonna split the covariate space into k equally spaced intervals or pockets. Okay, and then so what you do is you're trying to define this sort of like empirical conditional distribution. You're looking at like within the case market. This is how many observations are in the case market, and basically you're looking at how many observations are below key. And this is a conditional empirical CDF, and then you just maximize based on that, right? So this is why it's called empirical revenue maximization. And so what this is. Right, so basically you're looking at the value in this case interval, the case market, and then you just charge the price based on this PDK that you saw from this line here. Okay, so here's a little remark. If you ended up having a market that contains no observation, then simply choose the PDK to be PDK hat with any number, any arbitrary number in 0, 1. So asymptotically, this has no effects. Okay, that's what we show. So next is the further theorem. So this is upper bound. So I'm going to be using all this like what we call a less thing, a greater thing or something like that. And I think this is just big omega and big theta. It's part of the reason I think I do this stuff writing the statement because it's like when you follow this, it should be pretty long. So I guess so this is why I use this kind of symbol. Anyway, so the first result is if you do what I just talked, I was talking about the K market 3PD. That's give you the PD hat. If you basically looking at the revenue at PD hat, and then you looking at the revenue at the true distribution 3PD optimum. And so essentially this is a generalization error, or people call it regret sometimes. I guess you can bond this generalization errors by the two terms and the third term. So you can sort of ignore the third term. The short term is what people call it. It's one of those binomial tail bonds on this cardinality. On this cardinality. Oh, sorry. This is it's very difficult to spell, right? Yeah, so. Yeah, so I can just, where did I have this? Okay. So basically I have this exponential tail bound, which is on this cardinality. It's some kind of a binomial tail bound. Because you can ignore that chart really, because symptotically this will essentially, this term, the third term will be dominated by the first two terms. But I think the most important things are the first two terms, where this is kind of like a variance and the quotes. And the second one is like approximation error. The fact that you're dividing the interval into K markets instead of charging everybody at observed X value. So there's gonna incur some discreditation, I mean the approximation from discreditation, approximation error from discreditation, that's what it is. And the first one is variance because you're replacing the true conditional CF with the numerical CF, right? So what happens here is when you set the number of market into the quarter, that you optimize this the scale, this order that happens to be n to the half, n to the negative half. Okay, so I'm gonna talk about this later on. So you can rewrite the 1/2 is like 2 divided by 2 plus 2. And this 2 here, I'm just gonna use my hand. This 2 here actually has some, you know, it's the dimension come from, you know, there's I guess I probably should talk about this later on, compare this to the next slides, and it has something to do with the dimension when you, you're exploiting the actual dimension in this repeated trap, so that's something I'll get you later. Okay, so if you're just gonna look at the uniform pricing, and you wanna look at the revenue generated by the empirical, sorry, the ERM from, you know, for the uniform pricing, and then this is the revenue for the true distribution uniform optimal. And you're looking at this two difference in terms of the expectation, that gives you this upper bound. And this upper bound now, you know, I was trying to compare this with previous, you see this previous, there's a 2, and here there's a 1. That's sort of the intuition here, you know, is that here in the uniform pricing, you're just really based on the Y data, the validation data. While in the previous one, you're also exploiting, you know, the covariance. Okay, so that's where this tool from. So there's a curse of dimensionality from the fact that you are actually exploiting the covariance in the database 3. Okay, so sort of I was talking about the dependence on the dimension in 3PD. So the question is, can this be improved?
You're out.
I'm done.
You can wrap this up.
Okay, sounds good. So basically here's asking the questions is whether this dependence dimension in 3PD can improve. So that's those are the lower bounds. The lower bound is looking at a relatively large class of distributions like this holographic F, and then this holographic U for the marginal distributions, and then you're looking at the best price database, price discrimination, and database and uniform pricing. So we're gonna bound this from below, okay? So it turned out that you see that this is exactly the same base as our upper bound, okay? And this is for uniform pricing, that's the same rate as our upper bound. So in other words, our solutions that we talk about achieve that low rate of convergence in 3PD and uniform pricing we should expect. Okay, so sort of you might think that there's a first dimensionality from the fact that you have to exploit, you know, the covariance in the sample, you know, sample-based pricing. And so this is what kind of causes slow rate of convergence. And then here's a graph that kind of shows you, so you could have situations where 3PD actually performs worse than the uniform pricing if you have to make a decision. You have to charge the price based on sample. So that's a graph that kind of shows you that the story is that, you know, from the classic setup is not true anymore, that uniform pricing is actually doing better than 3PD. Okay. So the next one, so you think that, maybe the smaller sample size it is, and then, you're better off with not using 3D. And the story is also not true. So sort of the end of the story is that, you have to be kind of like, be careful with a very small sample. So we do have a example where we show distribution within the class, a big class of distribution we're considering, such as the two market ERN actually generate higher revenue than uniform ERN. But the sample size between the two, and that distribution is based on this paper. Two samples really better than one. So it's all kind of addresses the same kind of very small finite approach. So the last page, we're just gonna say really quick, there's a lot of future directions, but personally, I think the open problem I was kind of proposing in the previous page was to say, do you really have a regime where the K-market ERN strategy is always better than uniform ERN? I think it's gonna be a very difficult mathematical problem. It's based on sort of, what I kind of do. So there are other ways maybe that you can sort of try to address this open question of raising. So I was kind of saying, maybe looking at some symptotic case where the revenue gap tends to infinity as sample size goes to infinity. So there's kind of all sorts of things you can do.
Thank you.